So in a previous video, we talked about S3, and there were two ways to think about S3. One was as the permutations of the set containing 1, 2, 3, so the set containing 3 elements. And then the second one was as the symmetries of a triangle. And previously, we were able to generalize this point of view into the group Sn for n any number, well, any natural number, I guess. You can have S2 and S1. They'll just be the group of 2 elements in the trivial group. So it starts getting interesting at S3 and then beyond that. But right now, let's talk about the other way of thinking about S3, the symmetries one, and that will lead us to Dn. And so, in particular, a triangle, in the triangle we were looking at was an equilateral triangle, i.e. a regular polygon with 3 sides. So let's look at a regular polygon with 4 sides, a square. So I'll label the vertices. I've got this big square here. I'll label the vertices 1, 2, 3, and 4, and let's find the symmetries. So the symmetries will be, well, there's the identity symmetry, as always. And what else do we have? We can rotate the square, much like we rotated the triangle. So we can rotate like this, and we can call that element x. And of course, we can rotate twice. That'll be x squared. We can rotate 3 times. That'll be x cubed. And then if we rotate 4 times, we'll end up back in the identity. 1 will be back here, 2 will be back here, etc. So that's the rotations. And then now we can look at reflections. And if we look at reflections, maybe I'll erase this. So we can think about reflections. So one way to reflect a square is, vertically, like this, or I guess the line of reflection is horizontal, and the square gets reflected vertically. And you can have the opposite, of course. You can reflect like this, but you can also reflect on the diagonals, right? Yeah, you can reflect across either one of these diagonals. And so if we call this element right here y, so we can include y in our group of symmetries of a square, and then we can ask, can we write these other reflections in terms of these elements here? And the answer is we can. So for example, let's take x times y. So what'll happen with x times y? So if I have x times y, first I'm going to rotate. So 1 will go here, 2 will come right here, 3 comes down here, and 4 goes right here. And then rotating by, or not, instead of rotating, we'll reflect. So 1 and 4 will switch, and then 2 and 3 will switch. And so what are we left with? Well, 1 and 3 are in their original positions, and 2 and 4 have swapped. And so what we get is we've actually reflected across this line. So this reflection is xy. And likewise, you can do this for yourself if you want. We'll get, if we do x squared y, we'll get this. And if we do x cubed y, we will get that. So we'll have x squared, or xy, x squared y, and x cubed y. And those will be all of the reflections and rotations that we can get. And so in Sn, we had the following relation between our symmetries, which was we had, if you apply y, then you apply x, you get x squared y. Now that's not going to happen in the symmetries of a square. What will end up happening is if we have x cubed times y, that'll end up being the same as applying y and then applying x. So let's do that. If we apply y first, that will make us, well, first I better reset from to the original position of the vertices. Okay, so this is where they were. So first, to apply y, I'll swap each of the sides. And then we can swap 4 and 3, like so. And then I want to apply x, so I'll rotate. And to do that, we'll come down here, just like this. And what am I left with? Well, I'm left with 1 and 3 have swapped from where they were at the beginning, and 4 and 2 are back in the same place where they were, which is exactly this diagonal reflection, which is exactly xy cubed. So we have this relation right here. And so we can actually, so we call this the dihedral group. It's called D4, D3 being the same as the symmetric group. So the dihedral group is, by definition, the symmetry group of the regular polygon with n sides. So the dihedral group with 4 sides, D4, will be the symmetries of a square. And likewise, you can write down groups, D5, D6, D7, etc. This will be the symmetries of a regular pentagon, a regular six-sided polygon, seven-sided hexagon, I guess, and so on and so forth for as many as you want. And what will happen is, much like D4, you'll be able to generate the group with an element y, which is a reflection, a single reflection, and a single rotation. And you'll have the relation yx equals x to the n minus 1 y, where n, of course, is whatever is the n in dn. So that's dn.